Alright, in this video we're going to look at Kirchoff's rules. Robert Kirchoff lived a long time ago, specifically 1824 to 1887, just to kind of put you in history a little bit. And we know most circuits are going to be more complicated than just a simple series circuit, a simple parallel circuit, or even just a simple series parallel combination. Most real-life applications may have lots of different loops. They may have more than one EMF device. But there's a couple simple rules that can make these easier to analyze. The first one is called the junction rule. And the junction rule simply says the sum of the current in a junction has to equal 0. Basically, I prefer to think of it as current in has to equal current out. It's a direct result of conservation of charge. So, if we have a circuit, this is what a junction looks like. A junction's where two or more wires meet. If I have some current flowing into this junction, I'll call that I1, and I have two currents flowing out of this junction, I'm going to call those I2 and I3, then it's really obvious that the current going in is the sum of the other two currents. If you want to write it where they add up, where they equal 0, we would consider current going in to be positive and current going out to be negative, and that equals 0. These two are mathematically equivalent statements. The other rule is called the loop rule. And the loop rule says that the sum of the voltages around a loop has to equal 0. Think about it. If we pick a fairly simple one, you can think of it like if we have an EMF device and we put some things in our circuit, we'll just put some resistors. If we would add up this EMF voltage and this voltage drop across the first resistor, I'll call that V1, and the voltage drop across the second resistor, call that V2, that has to add up to be 0. Remember, V1 and V2 are drops, so minus V1 minus V2 has to equal 0. Now, most of the time, we're going to write that as the current going through R1 times R1. That tells you the voltage drop in the first resistor minus the current going through R2 times R2 has to be 0. It's as simple. This is a direct result of conservation of energy. As a charge goes through the battery, it gains a certain amount of energy. It loses part of that energy when it goes through the first resistor, and it loses the rest of the energy as it goes through the second resistor, because when it reaches this point, it has to have the same amount of energy that it had before. It's very much like if you climb a 20-foot ladder and you drop through a 10-foot slide, well, this must be another 10-foot slide because when you reach the ground, you're back to 0. You can't go up a ladder and go down the slides and reach the ground and be at a different height. You have to be back at ground level. Now, several examples. I like these problems. I know students often find them challenging. Because of that, we'll look at a little bit of a problem-solving strategy that will help, hopefully. And I think there's probably more of this in your book. As we go around a loop, keep in mind as we pass through batteries, we're going, if the current's going this way, we go from a low potential to the high potential, that is going to be a voltage gain. However, under some circumstances, what we're going to find is we may go where we're going from high to low. If we force current so that it actually goes opposite what we expect in a battery, where instead of going from low to high, which is what a battery normally does, it goes from high to low, we're going to actually have a voltage drop as we go through the battery. This one happens most of the time, but this one can happen in a complicated circuit. Typically, when we go through a resistor, we go from high to low. That's the direction the current will flow. That will give us a voltage drop. Again, that's the normal thing that happens. We go through batteries, we get a gain. We normally go from the batteries from low to high, and then we go from the resistors from high to low. We get a gain, we get a drop. Sometimes the current is going opposite of what we expect, so that when we go through the battery, we go from high to low, in which case we get a drop through the battery. If we happen to go through a resistor, will we go from low to high? In other words, this is like instead of sliding down the slide and getting to a lower ground, this is like climbing up the slide. You know the kid that climbs up the slide and going from low to high. If we do that, we will get a gain. Again, this one happens most of the time, and this one happens most of the time. When we do the examples, hopefully that we can kind of clarify when we get those exceptions. Oops. So let's look, this is example, I'm not even sure what the number is in your book, but it's about how to jump start your car. Something that I have not ever actually done. So normally your battery has about 12 volts in a car battery, but sometimes it goes dead. So let's draw a picture of what happens. This is plus, this is minus. And inside the battery of the car, there is some resistance. So we have a small internal resistance. So here's a battery. And this battery consists of a 12-volt battery with 2 ohms of internal resistance. When it's used to jump start, it's connected through some resistors to the dead or the weak battery. In this case, here's our other battery, minus, plus. This battery only has 4 volts instead of 12, and it's got 4 ohms of resistance. So this is kind of our other battery, just so you can see what's in the battery. This resistor right here is 3 ohms. This resistor right here is 7 ohms. Normally what I suggest, first of all, this one's fairly easy because there's only one loop. Okay. I think when you're trying to decide where to use the loop rule, I always start, this is my preference, you can technically start anywhere. But I recommend that you begin your loop at the negative terminal of the largest EMF, which is usually going to be a battery. So in this case, I'm going to start, I'm going to pick right here. I'm going to start over on this side. That's where I'm going to start. I know that in a battery, current normally goes from low to high potential, and then the rest of the circuit will normally drop all the way around. So you have to decide which way you think current's going to flow. I think the bigger battery will determine the current, so I'm going to assume that current flows in a loop like this. So when we go all the way around, we actually start and stop at the same place. So I'm going to start here, and I'm going to go around my loop. When I go through the battery, I gain 12 volts of potential from here to here. When I pass through the resistor, I lose IR. I don't know I, but I know R, so I'll put 2I. When I go, so now I've gone from here to here. When I go through this 3 ohm resistor, I'm going to lose 3I. When I go through this 4 ohm resistor, I'm going to lose 4I. But when I get to this battery, notice instead of going from low to high, this time I'm going from high to low. So instead of a gain, I'm going to lose 4 volts. I'm going to keep going, and I'm going to lose 7I. All of that should add up to be 0. We've got 12 volts minus 4 volts, so I end up with 8. I'm going to not write the V because V is a unit. It's not a variable. It might look like a variable, but it's just a unit. And then I've got 2, 3, that's 5, 9. I've got 16I. So I end up with 8 minus 16. I has to equal 0. When I solve for I get 0.5 amps. So there will be half of an amp flowing through this circuit. We can kind of talk our way through. We start here, we're at 0 volts. We gain 12 volts. At a half an amp, when we do IR, we lose 1, so now we're at 11. We lose 1.5, so now we're at 10.5. We're going to lose 2, so now we're at 8.5. We're going to lose 4, so now we're at 4.5. Oh, I did my math wrong. Let's start over. Somewhere I goofed. We're at 12 volts, we lose 1, so now we're at 11 right here. If I lose 3 times 1.5, if I'm at 11, I'm going to end up at 9.5. I had a math error. Okay, if I do 4 times 0.5, that's going to be 2 volts. So I'm going to go from 9.5 to 7.5. I'm going to lose 4 more volts. So when I get to here, I'll be at 3.5. and then 0.5 times 7 is minus 3.5, and I'm back to 0. We definitely did that one right. Let's look at an example out of the textbook. I'm going to do a couple examples out of the textbook. They get fairly complicated, but I think they're helpful. So here's problem number 52. Now problem number 52 has a 200-volt battery over here. We'll fill in the numbers in a minute. Here's our first resistor. Comes straight down like this. So 200 volts. This is the negative, this is the plus. This is an unknown resistor that we're going to come back and solve. In this branch, we have another resistor. We have another battery. This is a 40 ohm resistor. This is a 160 volt battery. It's the positive side, here's the negative side. And then over here, we have a third resistor. And it's 20 ohms. We're asked to find several different things. The first thing that they ask us to find is R. Now, I see 6 different loops. I'm going to start with this loop. I'm going to start right here at the positive, and I'm going to go around clockwise. But that's not the only loop. I also have a loop here in the middle section. I have a loop here in the third section. I have a big loop if I do the whole outside. I can do a medium-sized loop if I just do the loop around the first 2 rectangles here. Or I can do another medium size if I do it around the 2 rectangles on the right. Any loop, no matter which loop I pick, if I add up all those voltages, has to come out to be 0. But we're going to start right here with this easy one. I always like to start right here. So I go through the battery, I gain 200. I go through this resistor, and I lose IR. Oh, that looks like I have 2 things I don't know, and that's because I forgot to fill in one piece of information. They tell us that the current leaving the battery here, we can call that current 1, is 10 amps. That was given. So I've got 200 minus 10 times R equals 0. And I pretty quickly can solve and go, oh, well, now R has to equal 20 ohms. That makes sense because look at this point right here. This point has to be 0. Notice it's going to be 0 all along here. There's no resistor between here and here. This has to all be 0 too. There's a big stretch of this loop where our potential would be 0. All right, let's do the second question. The second question says, find the current through the 40 ohm resistor. So we need to pick a loop that has the 40 ohm resistor. To me, the obvious loop to pick is this middle one. And again, I'm going to start at this, since this is the only battery in this middle loop, it's negative here, and I'm going to start right here, and I'm going to assume that my current flows this way. So the current's going counterclockwise this time. So I go through from here as I pass through the battery. I'm going to gain 160 volts. And then when I pass through the 40 ohm resistor, I'm going to lose 40 I. That's my I times R. That's the only thing. There's nothing anywhere else around here. So if I solve that has to equal 0, I get that I has to equal 4 amps. The way I've drawn it, I have 4 amps going this way, and the way they told me I have 10 amps going this way. That kind of tells me that if I were to draw right here going through both of this, if there's 10 amps coming this way and 4 amps coming this way, that's 14 amps right there. Here's another thing we know. If there's 10 amps going out of the battery, there has to be 10 amps going into the battery. Okay, we've answered parts A and parts B. Let's look at part C. C says, the power supplied oh, no, it doesn't say that. It says, find the power supplied by the 160 volt battery. Now, we know that the formula for power is V times I. But look at the picture. We know how much current's going through the 40 ohm resistor, but we don't know how much current's going through the 160 volt battery. We need to do another loop. I'll do this loop in red. We need to start here, and we need to go through that battery and go through this third loop. All right, so we gain 160 volts. We lose 20 times I when we pass through this. So minus 20 I. So if I think of this as being I3, I could think of that as I2. They told me I1 was 10. That has to be 0. Well, when I solve that, I get I3 is 8 amps. But notice I drew it going this way. If we use our understanding of the junction rule, if I have 4 amps going to the left and 8 amps going to the right, this in here feeding into that has to be 12 amps. There's 12 amps in, 4 go to the left, 8 go to the right. So the power that's going through that battery is actually, the current actually has to be 12 amps. So when I do VI, I get 160 volts times 12 amps is 1920 watts. Or since we probably have 2 significant digits at the very most, I'll put 1900 watts. This is one of those problems where they really only gave us 1 digit. I wouldn't be upset if you put 2000 because they really didn't give us clearly 2 digits everywhere. Now, anytime I do a problem like this and I had 3 things to find and I did 3 loops, I kind of like to do one more loop as a check. I could do a loop that included just 2 out of 3, but I'm going to do the big loop. I'm going to start here. When I do the big loop, oops, that's not what I wanted to do. I usually just go all the way around. So I'm going to start here, and I'm going to go all the way around like this, with the current going out of the biggest battery and then back into the biggest battery. Need to be really careful. I pay attention to my signs. So this is just sort of a check. I go through the big battery, I gain 200 volts. And I don't want to write the volts because it looks like a variable. I'm just going to put 200. Minus, when I go through that first resistor, which we decided was 20 ohms, there's 10 amps going through it. So 20I, which is 10, there's my first voltage drop. 20 ohms, 10 amps. I keep going. Notice when I get here, my loop is going clockwise, but this current is going to the left. If I'm going opposite the current, that's when I subtract for a resistor. So instead of subtracting 4 amps times 40 ohms, this time I have to add. Whoops, let me make this all a little smaller. There we go, so you can see it all. So minus IR, I is 4, R is 40, but I have to subtract. I have to add because the current goes to the left. I'm going to the right. So this is really low, and this is high potential. I'm going through the resistor opposite the normal way. And then I get to this last little part. This time I'm going back with the current. So minus 8 times 20, IR. So minus 8 times 20. And then that's it. There's no more resistors. I go all the way back around. That better equals 0. Well, it clearly does. There's 200 minus 200 plus 160 minus 160 equals 0. It takes a little practice. They really do, but it's kind of like once you learn how to do them, they're kind of fun, like puzzles, if you like solving puzzles. Let's do one more. Let me check and make sure I know. This is problem 54 out of your textbook. Okay, and 54 looks like this. We have a resistor. We have a battery. In the middle here, we have another resistor. Oops. Along the bottom, we have another battery. And another resistor. Some of this, they've given me numbers. This is a 15-volt battery. I'm going to call this R1 just so we can talk about it, and it's a 7-ohm resistor. Call this one R2. It's a 5-ohm resistor. Call this one R3. It's a 2-ohm resistor. This is an unknown EMF device. They also drew 1 meter in here. A meter that's wired in like this, and we haven't really talked about meters yet. We're going to talk about them in the next video. But that's an ammeter. It's designed to measure the current. So it would measure the current through this top branch. It would measure the current going through the 15-volt battery and the current going through the 7-ohm resistor. All right, here's the given information. Current flows through the 5-ohm resistor and it consumes energy, which means it uses energy. That's what resistors do, at 20.0 watts. They want us to find the unknown EMF, and they want to know what the ammeter reading is. All right, that 5-ohm resistor, the one that's located in the middle, is using energy at 20 watts. We know that power is VI, but we also know that if we substitute V equals IR, we get the fact that power can also be found using the formula I squared R. So we have 20 watts equals I squared times R, and R is 5. If I divide by 5 and take a square root, I see that my current has to be 2 amps. Now that's not the answer to the ammeter. That's the current going through here. Now, we really don't know for sure which way the current flows unless they tell us in the picture, which they do. They tell us that the current is going this way, so they're trying to help us out. So I say we solve for that top loop first. If I want to solve the top loop, that's going to work pretty well because I can start here. I can go in the direction of the battery flow from low to high. And then when I make a loop, I'll be going in the correct direction because they said the current goes this way. All right, so let's do that loop. We're going to gain 15. We're going to lose I times R, which is what we're trying to find. I times 7, so 7I. And I'm going to erase that volt again because I think it looks like a variable. So we've gained 15 volts. We're going to lose 7I. When we go through the battery, we're going to lose 5 times 2 because the current through the battery, this current, is 2 amps going through the battery. By the time we finish going around, there's no more resistors. That should equal 0. So I have 15 minus 7I minus 10 equals 0. That gives me 5 equals 7I. And I is equal to, I get a decimal, 0.714 amps. So the ammeter reading is that 0.714 amps. Right, we know some pretty interesting information now. Let's look at what we know here. Look at this junction right here. We know we have 0.714 going in, and we know we have 2 amps coming out. that tells me I have to have current going in right here also. If I do, 2 amps minus, keep touching my screen, minus, why does it not 0, hang on, let's see if I can get this thing to settle down. 0.714, I get that this should be 1.29 amps. So this is 1.29 amps. All right, let's do this loop. Let's make the assumption that this is negative and this is positive because we know the current's flowing this way. So if we start here, we're going to just kind of go around this loop like this. My equation's going to look like I have E. When I go through this 5 ohm resistor, minus 2 times 5. When I go through the 2 ohm resistor, minus 2 times 1.29, because this branch down here has to be 1.29. That has to equal 0. If I solve for E, I've got E minus 10 minus 2.58. I get E equals, that's 12.58, but remember I only have 3 significant digits. So E is 12.6 volts. We couldn't have done that if we hadn't been given enough information to get started. And we needed to analyze this junction. We needed to figure out that if I know how much current is in this top branch, and I know how much current's flowing through the middle here, I can figure out how much current is flowing in this direction. Okay, I don't have any more examples ready to show you, but I feel like we will want to work some when we are all together. So I'm going to stop my lesson on Kirchoff's laws right here.